We're getting started here with our brand new Kepler's Laws study guide. We know there are 3 Kepler's Laws, and we want to be able to use those laws to answer and elaborate on our unit question. Do all objects in the universe, both natural and human-made, follow an orbit similar to Earth? And if so, what are those similarities? What do we know about orbiting objects? So when we think about natural, hopefully what comes to mind are things like planets, asteroids, comets, maybe moons. And then when we're thinking about human-made, we've got satellites and space stations, things that people have launched into space that are still orbiting around different objects. So as we think about our unit question, we of course have our activities that we're getting done, starting with this one, the big E. And E is of course for ellipse. We made 2 elliptical shapes on our paper for this activity, kind of dissected them a little bit, and of course an ellipse is that oval shape. Typically what we've done so far with our debriefs is I've said, hey, bullet point 1, do this. Hey, this diagram, draw it in. We're not going to so much do that today. I'm going to switch over to my slides, and you are going to write down important details that seem to click with you. And, I'm going to point out a couple big ideas and maybe star and highlight them up on my screen. So that might be a good signal to you. Oh, that's maybe something I want to record. So again, here with our big E, our E is for ellipse, and that is of course, this shape over here. We know all orbits follow this elliptical or kind of squished circle shape. That's our ellipse, and this of course is a circle. We don't see orbits that go in that circular shape. But the other big thing we want to think about with these ellipses is where exactly would the sun be in these elliptical orbits for something like a planet in our solar system, like Earth. We know for a circle that sun would be right at the midpoint, the center. But as far as an ellipse goes, you might recall in our activity, we didn't have just one center point, we did have 2. And those are known as the foci, right? Every ellipse has 2 foci, and they fall right on that long distance across the ellipse known as the major axis. So these 2 foci points are within the ellipse, and one of them has to be the object that the planet orbits around, like our sun. So if you haven't written or drawn anything yet, a good thing to start with would be this. Orbits are an ellipse, and we end up with the sun at one focus point, or one foci. Remember, that's the word for more than one focus. Circle over here would have one focus. Ellipse has 2. And the tricky thing is this other point right here, it's nothing. It's there mathematically and gravitationally. It's not an object. And I did get some questions also with the sun. It doesn't always have to be the left or always have to be the right. It depends, right? So ellipse is that oval shape, 2 foci, and the sun at one of them. Now what we also know is that no 2 ellipses are necessarily created equal. Those foci can be different distances apart. The object on the foci, like the sun, can be different masses, and so that impacts what the orbit is like. And when we think about how different those ellipses can be, the word we come to mind is eccentricity. That was a vocab word from our activity. It's thinking about the variation that orbit has from a perfect circle. So again, we don't see orbits in a perfect circle. All of them have some amount of eccentricity. They're all off a little bit from a perfect circle. So this is a great visual showing us if that ellipse is closer to 0, it is more circular. If that ellipse is closer to 1, it is much more stretched out. And you calculated, I know, many eccentricities in your big E activity, and Earth was one of them. Its eccentricity falls right in here, 0.017. So when we think about what the Earth's orbit is like, it's pretty circular. It has a slight variation from a perfect circle, so it's got a low eccentricity. We want to keep in mind those values. Like we said, close to 0 is more circular, close to 1 is more elliptical or stretched out. Now, most planets are within this range for eccentricity. You had 2 of them on your list that were in this range, Mercury and Pluto. And then we did have one object that was way down here at 0.967. And you might remember that's Halley's Comet. So I just want to show you what that really looked like. So it's pretty cool. You know, here's all of our orbits around the sun. And at first glance, look how circular they do appear, right? But when we were to measure them and calculate them out, they are elliptical. They have some slight eccentricity to them. But Halley's Comet hopefully stands out to you as a very elliptical shape, right? The sun is one of its foci, and that means the other one has to be like way over here. So those 2 foci are very far apart, and we have this very long elliptical shape. It's about a 75-year orbit time, where of course the Earth is at 1 year. Now, Halley's Comet is approaching its farthest point in the orbit. We know that word as aphelion in 2024, so coming up. So the projected return for the comet is in 2061, back to its perihelion, which we'll be able to then see from Earth without a telescope or anything. So pretty cool. So back to this eccentricity. It's measuring, again, the variation from a perfect circle, so how off an orbit is from a perfect circle. And I know you did a lot of calculations on this, and you did that by using these 2 numbers, distance from perihelion to the sun. So when we're thinking about the orbit, we're realizing how close the planet can get to the sun. And of course, aphelion, like we said, how far the planet can get from the sun. So we did those measurements for ours. I gave you the measurements for the planets. And from there, we did a couple formula plugins. So those 2 values got subtracted, perihelion and aphelion. Those 2 values got added together. And then the result of those 2 were divided out to give us our eccentricity over here. So all we need to calculate eccentricity would be these 2 values, and of course our formulas. So last big idea to think about is within this elliptical orbit that we have, we can never really give an exact distance from Earth to the sun. And that's because 2 things. One, the Earth is always moving, right? It's always going around that orbit. And 2, that orbit shape is an ellipse. And so because that orbit shape is an ellipse, every time something or motion happens, right? This is a distance, this is a distance, distance, distance. We're seeing that distance change all the time. And because that distance is constantly changing, for not only the Earth, but every planet, we have to give the average distance from the planet to the sun, because every single day it varies. And just a heads up, a little bit of background, which is pretty cool. Here at our aphelion, we are 94.5 million miles away, and here at our perihelion, we're 91.5 8.4 million miles. So again, those two average out to around 93 million miles. That's the standard distance that we say the Earth is from the sun. And again, you're going to get that for every planet. The distance given in an average, because of the elliptical orbit shape, there's never an exact distance. It's constantly changing because of its motion and the fact that our orbit is an ellipse. So again, we weren't doing directed notes, bullet points here or there, but these were the big ideas I hope you grabbed today. What shape are all orbits, and where do we see the sun within those orbits? What do we know about eccentricity? You should be able to define it. Talk about what eccentricity of a 0 is compared to a 1, what that looks like, and then just know what's needed to calculate it. Again, we didn't do any calculations here together, but you did many on your assignment, and you'll be asked to do some more again. And finally, what do we know about that distance of planets from the sun as they orbit around? Why does it have to be given as an average versus an exact amount?